Hello everyone. So this is the first lecture of our course EEE 4705 microcontroller based system design. So in this lecture we will try to learn about some very basics of computing, so some fundamental concepts that are needed to understand what we plan to learn throughout this semester, which is microcontroller and architecture of it. So what we are going to do, we will try to learn about 8051 microcontroller throughout this semester. So to understand any kind of microcontroller or microprocessor, we need to have some very basics of how it actually works, right? So this kind of things will be discussed here in this lecture, and throughout this semester we will try to follow this book, the first book by Muhammad Ali Majidi, and if any more resources are needed, I will obviously provide you through lecture slides and videos. And also, like here we have also taken help from the second book from Manish K. Patel. So like this, time and time again, maybe there will be more resources that I will cover, but they will be provided through lecture videos or lecture slides. Okay, so here also, if we talk about the first lecture, which is introduction to computing, I am just following the book from Majidi and trying to cover the first chapter of that, which is called Introduction to Computing. So if you look at the book, you will see that the first portion of that chapter is quite straightforward, and you have already gone through the stuffs in previous semesters, like section 0.1. This is actually just conversion of different number systems, basically from decimal to binary or binary to hexadecimal, these kind of things. So I think we already know about these things, so I won't cover those in this lecture. And also some of the basics of gates, logic gates. Okay, so very basic things. I don't think we should cover those in this lecture because you are fourth year students, and if you think you don't remember all of the things from those topics, you can go through those things from the book. But I will start for this lecture, I will start from section 0.3. okay, section 0.3 of chapter 0. So as I said earlier, to understand microprocessors or microcontrollers, we need to first understand some very basic concepts of how internally computers work, right? So for that also, I think I had given you one instruction in the Google Classroom that you should go through that video we covered in third semester digital electronics lab, which was where we discussed about the architecture of 8-bit computer, one example of 8-bit computer, SAP1, simple as possible one. So I told you so because most of the things we will discuss here also, you will see that they're similar to SAP1. Whatever fundamental concepts I will try to discuss here, you will see that a lot of things are quite similar. Here we will see that maybe the concepts are same, but maybe they are implemented in a complex way. So that's why again, before you go through this video or watch this video, I will request that first go through that video, and after that come to this video and try to relate. I will try to relate each and every concepts with that video and with those architectures, with that architecture of SAP1 and how they actually are similar, so that you can understand. Again, before we start, even in section 0.3, I think there are some things which I don't think I should discuss here. Some important terminology, basically, like what is bit, byte, nibble, word, these kind of things, and also how much is a kilobyte, megabyte, or gigabyte. I think most of you already know those things properly, but if you don't, you should go through these things, because throughout our semester, maybe they will be helpful. This knowledge will be helpful in different math problems as well. So try to go through those particular portions. Then if we start from here, so basically we were looking at a very fundamental level of breakdown of what are the components needed to build a computer, right? So there are four major components: CPU, memory, input output unit, and also a system bus, right? So for each of these components we will try to go through and try to discuss about some of the concepts, but before that, I think first of all we need to understand what is the difference between microprocessor and microcontroller. This is a microcontroller course. In the last semester you took one course where we covered microprocessors. So here you can see we have four different components. They are actually connected with each other, basically with the help of the system bus, right? But how we distinguish between microprocessor and microcontroller is that, in microprocessor you will see that with the CPU, all the other components like memory, that can be RAM or ROM, and different input output units, these are connected externally with the help of this bus, right? And for the case of microcontroller, what we will see, everything is actually built in a integrated circuit, right? Everything will be in one chip. But for microprocessor, we are going to see that this CPU itself, this is can be found as a chip, a IC. But if you want to make this microprocessor work, you must connect memory, input output unit, and different other things to make it work. That is the main basic difference between microprocessor and microcontroller. And also another question there can be is, what is the difference between microprocessor and a CPU? So basically they are the same thing. CPU is the architecture, but whenever we are talking about microprocessor, we are just implementing a CPU in a chip, in an integrated circuit IC. So then that will be called a microprocessor. That's the only difference, but architecturally they are the same thing. So let us try to understand each of these component briefly in this lecture. So here in this picture you can see like where we have a detailed view of the previous picture, basically. So this is the microprocessor and different kind of memory devices. RAM and ROM are here connected with microprocessor. Input devices and output devices are connected using different kind of buses, right? And one thing what I will try to do throughout this lecture is each and every thing I will discuss here, I will try to relate everything with that SAP1 lecture, the architecture of SAP1, and how they are kind of similar, right? So I have started with the discussion of bus first. So as you can see, they are saying that the main purpose of having a bus is maintaining the communication between different components here, right? Like microprocessor must communicate with different components like RAM and ROM, and also input and output devices, right? Otherwise it cannot work. So that's why we need this communication path, and these buses actually help us for that. Like if you remember about a SAP1, we had only one bus of 8 different lines, right? 8-bit bus. And that was the only bus where everything was happening. That was a general purpose bus. So if a data was coming, that was going through that bus. If an instruction was coming, that was going through this that bus. So only one bus for all the communication. But here we are going to see that we have 3 different separate buses for maintaining this communication, and each of the buses have a specific purpose. Just that, right? So here you can see we have 3 different type of bus: address bus, data bus, and control bus, for maintaining the communication between these other 3 blocks, right? So let us start with address bus. So this one is actually the address bus, right? So address bus is actually just a group of wires to identify specific memory location within a memory chip, or it can be input output devices. Okay, so identify different specific memory location. Try to remember that. So what that means, so just for now, let us discuss about different memory devices. Maybe we can discuss about input and output devices later on, but if you think about a RAM or ROM, from our SAP 1 also we saw that in our RAM we had (16 rows like this, right? Something like that. So started from 0 up to basically 15, right? So 15 different rows were there, and each of the rows contained 8 bits. So basically 16 by 8 RAM that was, right? So we could actually address different locations here, that means different rows here, using the help of memory address register, if you remember correctly, right? So we could actually point to a different location here, different row here, and try to fetch data or write some data there in that row. So we are calling memory location, basically that is what memory location means, and each of the memory location can have different amount of memory. Like for the case of SAP 1, that was 8 bit. So in total we had 16 different lines or rows, each of them had 8 bit of data, right? So address bus here basically will try to locate those. Okay, so identify different memory locations, and also we will see that different input or output devices can also have very unique address. By using that address we can look at different input or output devices later on throughout whenever we go in the last portion of this semester, we will see that. So another thing also we have to understand that the direction of different buses, right? Like for the case of address bus, you will see that what happens is microprocessor will send a different address to locate different memory location in RAM or ROM, or it can be different input devices or output devices. So always the signal is coming from microprocessor to locate different memory location, never from RAM to microprocessor or ROM to microprocessor. That's why the direction for this particular bus is unidirectional. Then also another thing is you have to understand whenever we are talking about buses, they are just wires, right? Like for our case of SAP 1, there were 8 different wires to communicate. So here also we are going to see 8 or 16 or maybe 32 number of wires that are facilitating this communication, right? So what we are saying, like just for a simple example, in our SAP 1 we had 16 different lines for the RAM. So if we want to address or be able to address each of the rows there, we should at least have that facility, like all of the separate locations can be identified with a different address, right? So that means for that 16 rows what we had was 4-bit memory address register, if you remember correctly. So this 4-bit means using this 4-bit we can actually have 16 different combinations or 16 different values possible to identify 16 different locations in that RAM, right? So something like 2 to the power 4, am I right? So similar thing is here can be done, if an address is x bit wide, that means there are 2 to the power x different addressable memory location, right? If this is 8 bit, that means we can address 2 to the power 8 different memory locations. So basically if you have wider address bus, that means you can address more memory. The RAM size of the RAM or the size of the ROM can be higher based on the size of the width of the address bus. So generally what we are going to see that for each of the memory location, the size of data is 8 bit or 1 byte, we can say. For our case of 8051 microcontroller, this is the value. So we will see that our memories will have 8-bit for each of the memory locations. So if that is the case, for that example we can say if a microcontroller has 16-bit address bus, that means we can address 2 to the power 16 or this amount of bytes, right? Then let us talk about data bus. So after we have addressed a specific memory location, we can either fetch the data or write some data in that location. So for that, to transfer any data to a particular memory location, or maybe let's say to this output device, we want to write some or show some, display some data, or we can also take some data from these input devices. All of these are possible through the help of data bus. Okay, so also another thing you can say that the direction of this particular bus should be bidirectional, because both the data can come from CPU to different devices, as well different data can come from these devices as well to the CPU. So both direction is allowed. And also another thing is maybe this discussion is not properly understandable right now. I will briefly still talk about that. Like for the case of RAM, you can see this direction is bidirectional, right? Like here the direction is from input device to the CPU or microprocessor. Understandable. Always the signal should come from input device, never from microprocessor to the input device. And also for this output device, the direction should be from microprocessor to the output devices. For the RAM, you can see we have bidirectional situation, but for the ROM we have unidirectional situation. So for the case of ROM, this is from the ROM to the microprocessor. Now for the case of these computers, microprocessor or microcontroller, what you have to understand, ROM is basically used for storing the instruction, our program which we want to run through the help of microprocessor, that is stored on ROM. And from that, microprocessor or CPU try to fetch the instruction and try to execute those line by line, one after another, right? But never something like that happens, like CPU will send some data to the ROM to write new data to ROM. ROM cannot be modified by CPU, but we can have external means of modifying ROM. That is possible. That is how we burn or store different programs onto the ROM, so that that program can be run by the CPU. So that's why we have this direction here. But for the case of RAM is random access memory. So what happens whenever the CPU is trying to execute any kind of instruction, it takes help from RAM, sometimes by putting some value onto the RAM, and sometimes taking some value that it has already stored onto the RAM and taking it back to the CPU again. So in this way, bidirectional communication happens between the RAM and CPU. That's why we have this direction here like this. Another thing is very important, like you will time and time again you will hear this particular term called 8-bit microcontroller or 16-bit microprocessor. So what is this thing means? So by this 8-bit or 16-bit, what it basically means is the amount of data that can be processed at a time by that particular computer. So basically higher the number, processor will be that much fast, and it is not dependent upon just one thing. Like we cannot say if this component is 8-bit, then we can say this is 8-bit computer or something like that. Nothing like that. Basically different components are designed in such a way so that that amount of data can be processed at a time. Like if I talk about 8051 microcontroller, that is 8-bit microcontroller, right? So that means 8-bit can be processed at a time, right? So obviously bus is helping for that. We have 8-bit bus for 8051, and also different other components are also designed in that way. Like ALU for our 8051 should be 8-bit, right? So basically it actually gives us some idea about how much fast is that computer, and here data bus helps about that, right? So like an 8-bit bus can send out 1 byte at a time, but 16-bit bus can send out 2 bytes at a time, which is twice as fast. So if you have wider database, that will help you to send more data at a time, so faster, right? Now the last one, control bus. So for control bus, basically here, so this is the simplified version of control bus. So what it does basically is, whenever you are trying to communicate with, let's say, RAM, either you want to write some data to the RAM or get some data, fetch some data from the RAM to the CPU, right? So that's why we have this signal, either read or write. We will try to give that signal so that the modules can communicate in that way. So either fetch data or write some data there, right? Okay, so let us discuss about CPU. So here you can see this is a general block diagram of a CPU, and also I have kept this block diagram of SAP1 for convenience. So we will try to compare with each other and try to understand how they are almost similar to each other, right? Different components are almost similar for the case of CPU, which we need to understand, and the one we learned or earlier in 3rd semester. So you see, one of the components is actually program counter, PC. We also had a program counter here in SAP1. So the idea of having a program counter was it contains the address of the next instruction to be executed, right? So basically after each instruction was executed, it incremented its value to point to the next instruction. So in this way, one by one, each instruction was getting executed up until the end. So that was the idea of program counter. So similar kind of components will be there also for our case of CPU. It can be microcontroller or microprocessor, so we will have this kind of components. And also in the last semester, I think for 8086 microprocessor, you learned about a similar kind of thing, but the name was different, which was, I think, instruction pointer. Okay, so instruction pointer and program counter are almost similar, same thing. So they just point to the next instruction to be executed. Then let us talk about different type of registers we have, general purpose registers that are embedded inside the CPU itself. So what you have to understand, like for the case of microprocessors, we said that the memories are separate from the CPU and they are externally connected, for example RAM and ROM. But even after that, there are some memory, very small amount of memory that are embedded onto the CPU for fast operation. Okay, so these general purpose registers are basically what helps us to do different kind of arithmetic operations, right? So here also you saw that we had B register, or here accumulator, sometimes it was called register A, and these kind of registers are basically the kind of registers we are seeing here. We have different registers here. Maybe in detail for 8051 we will try to learn what are the registers we have inside the CPU, but they help us for faster operation. Then let us talk about what this one, instruction register. So we had similar kind of components here. It just temporarily contains the code for instruction, right? So different instructions are first was kept here, then from there it was going to the controller sequencer for decoding purpose, right? So here the same thing, similar kind of thing here. So you can consider this one similar to the controller sequencer. In the controller sequencer, if you remember correctly, we had a decoder unit which actually was decoding different instructions we had in our dictionary, like add, sub, mul, then there was halt, this kind of thing. So basically first it was getting decoded, and based on that we had some control signals, these kind of control signals which were sequentially was getting changed so that we could control all the components we had here. All of them were actually getting signal from this controller sequencer, these bits. So similar kind of thing, this this timing and control unit will do to control the other components of the CPU. Okay. Then arithmetic and logic unit. So you already know, just for different mathematical operation, arithmetic operation, we use this ALU. We had the similar kind of thing in SAP1 as well. And then finally this stack pointer. I don't think we don't have enough knowledge to understand stack and stack pointer right now, so I am skipping that for now. Maybe whenever we go to that chapter, we will try to understand how it is stack and how stack pointer helps to that, right? Okay, so this is the general depiction of a CPU. I think briefly we can understand how it works. And next, let us talk about memory. So because we have different kinds of memory, like some of them are inside the CPU itself. We have RAM, which is, you know, random access memory, and we have ROM, read-only memory. We can only read. So you will see we will have different kinds of memory in microcontroller. So right now, if we try to go to the details of each of them, it will be very difficult right now. So we will just try to generalize this memory module into this discussion here, so that we can understand briefly how it works inside a computer. Okay, so generally, let's say for example, if it was a ROM, or a RAM, it should look like this, just like the RAM we had in SAP1. So different lines should be there, starting from address 0 up to the last address. So here you see from 0 to n-1. So we have n different memory locations here, and each of the memory locations have different amount of data. Like for the case of here, 1 2 3 4 5 6 7 8, so 8 bit per memory location. So in this way, memories are laid out, and if you want to access some data from here, first of all you have to address a different location here using the, you know, address bus. So here you can see this bus, this thing will be connected with address bus to locate to a different memory location. And after that, what we have to do, we have to give a signal, like either we want to read or write signal to that location, that we have to give first. Then that data will be either going out or going in for the memory. So this is the generalized idea for memory inside a computer. Well, finally, we will try to look at one example program to understand how internally a program can work and everything is executed. So an instruction is faced, then executed, how it is done. We will try to understand through this example program. So first of all, let us try to understand the configuration of the computer we are working with. So let's say we have an imaginary CPU which has 4 different registers: register A, register B, register C, and register D. And it has 8-bit data bus and 16-bit address bus. Okay, so therefore the CPU can access a memory from 000 up to FFFH. This is important, like FFF, this is obviously hexadecimal because we have a H sign here, right? Basically you can also write this in this way, right? 1 1 1 1 1 1 1 1. This is also possible, right? So this is the last location. So because this is binary, we can write a B there. So by this is hexadecimal, we are meaning this is the last location that can be accessed by the CPU, right? Because this is a 16-bit address bus. And the action that we want to be performed is this one. Okay, so step 1, we want to put a hexadecimal value which is 21H hexadecimal into register A. Then step 2, with the value we already have on register A, we want to add value 42H. Then third step, because already in register A we have accumulated some data which is 21H, with that this value will be already there, and with that we will add another value which is 12h. After doing all that, we will try to halt or stop the code, right? This is our task here. And another thing you have to understand here, for each of the task, we have some instruction, right? Like it is called opcode. Maybe later on we will try to understand what is actually opcode. Just understand that we are assuming the code for moving a value to register A is BOH, which is 8-bit, right? So this is the instruction or code for just doing that. Maybe how or which value we will actually move, that will be defined later, or actually is defined here. We will try to look at the whole code, but understand just for moving a value to register A, the code is this one, and also for adding a value to register A, the code is this one, 04H. Okay, now if we understand this much, now maybe we can look at the whole code. So for the instruction we already have here, this should be our code, right? So one by one, let us try to understand. Like, move value 21h into register A. To move any value to register A, the code should be B0H, right? And the value we want to move is 21h. So for that, this is the data. So first of all, there will be the code and then the data. So opcode and then operand. So maybe in the next lecture we will try to understand what is opcode, what is operand, what is mnemonic, this kind of thing. But this is the general, format of the code we have to understand this program. And then the next one is add value 42h to register A, which is what? This is the code as we seen here, and the value to add is 42h, so 42h. For the next one also similar thing. This is the code to add any value to register A, and this is the value we want to add. And also for halt, we need to have another code, right? I think F4H was the value, yeah. So even though it's not written, for halt the code is F4H, and for halt we need we don't need any kind of data here because we don't need that, right? So for the one where we want to halt the whole program, the code should be what? F4H, and here nothing is needed, right? So this is the overall code we have. Now before we want to run this program using a CPU, first of all we have to store that data in any kind of memory, right? That can be ROM. So in the ROM, let's say we are trying to store this data, and for ROM each of the rows will have some address, right? Memory locations. So we have to start from any memory location to store the data. So let us say the starting memory location we have selected is 1400H. It is arbitrarily taken for this case, you can assume. If that is the case, how this data will be looking inside a ROM, let us try to understand. As I said, in most of the cases 8051 will have 8-bit length for each of the memory location, right? So if that is the case, we cannot actually store a whole line of code in one memory location, because this one is actually 8-bit, if you understand, and this one is 8-bit. So in total this whole code, this line of code is 16-bit. But if we talk about the ROM of a computer like we have 8051, the ROM has, each of the memory location actually has 8-bit of space. So that means what we have to do, starting with 1400H, we have to store first 8-bit of the first instruction, and the next 8-bit should be stored in the next location. So in this way, you see, two locations are storing one of the instruction, two locations are storing one of the instruction. So in this way it's happening. And for the last one, because we don't have any kind of data for that one, halt instruction, we can store that in one place, I mean one memory location. So in this way, starting from 1400H to 1406H, we have stored our program to be run by our CPU. Okay, now let us try to understand how this program will get executed by the CPU. So we have three tasks at hand. Let us first start with the first one, which is move value 21H into register A. So these are the two lines of code we are trying to actually execute, right? So first, how it will start, the program counter, which is 16-bit, because we have 16-bit address bus. So program counter also has to be 16-bit because it points to a address to the ROM to fetch some data from the ROM. So it has to be the same length as that address bus, right? So that's why program counter 16-bit, which is gets set to 1400H. This is the address of the first instruction to be executed. That's why it should be set to 1400H first, and then what will happen, it will go to the CPU, and CPU will actually put this particular address to the address bus, so that this particular location onto our memory can be located, right, which is this one, right? So we want to actually fetch this data from the memory, from the ROM. So that's why it puts the data on the address bus, and then finally what happens, then we will see that the memory circuitry, there will be different circuitry which will actually, using this address bus information, it will try to find the memory location, and at the same time CPU using the control bus will activate the read signal. So read signal is there, address bus has identified a particular location inside of our memory. So this memory will send this data to the CPU through data bus. Okay, so contents of the memory location, this location, will be sent to the CPU through the data bus. So this is basically the content, so it will be sent through the data bus to the CPU. So CPU, after getting the data, it will try to decode by the help of instruction decoder. So just like your controller sequencer, in our controller sequencer we had an instruction decoder portion and then control circuitry. So instruction decoder will decode the signal, decode this instruction, and the instruction is actually bring into register A the byte in the next memory location. Okay, so whatever information or 8-bit data you get in the next memory location, which is 1401H, bring that and store that into register A. This is the instruction, right? So based on that, now CPU understand, and CPU will command its controller circuitry, which is, after the decoding part, we had in controller sequencer controlled different portions of the SAP1 using different bits. We had 13 different bits. So similar thing here. So CPU will command the controller circuitry to do that, to make this happen, right? So after that, what will happen, the value we have in 1401H location, this one, which is 21H, this will be fetched from memory to the CPU. So similar kind of thing will happen. Again, what will happen, I am not showing everything here, but first of all, the address bus should send the proper address, which is 1401H, to the ROM, and then obviously read signal has to be activated through the control bus using the CPU, and finally the data we have here in this particular location 21H should be going through the data bus to the CPU. In this way, it will go to the CPU, and CPU will store that data to register A. So multiple registers are there in CPU, but all the doors of other registers will be turned off at that moment. Only register A will receive the data. In this way, the task is completed. The first task is completed. Next, let us look at the second task. Add value 42H to the register A. So after completing the first instruction, program counter now has to point to the address of the next instruction, which is 1402H, right? So it has to increment by 2, which is kind of different compared to your SAP1. So in your SAP1, the program counter was always incrementing by 1 because all the instructions were at most 1 byte in length, right? But here you can see this instruction is actually 2 bytes in length. That's why after completing the first instruction, it has to increment by 2 so that we reach this value or try to fetch this value, right? So that's why it has to increment to this value, and after that it will send that data to CPU, and CPU will put 1402H onto the address bus, and from the memory location 1402H it will fetch the code 04H, right? Just like before. So address bus will point to a particular memory location, then read signal will be activated, and through the data bus this particular data will be sent to the CPU, because here we have this value stored. This is the instruction. So after getting this data, CPU will try to decode this instruction by the help of instruction decoder, and the decoded instruction is bring the value from the next address, which is 1403H, and add it to the contents of register A, right? CPU will instruct the control circuitry to do necessary things so that this function is done, right? So after that, whatever we have stored in the next address, which is 1403H, we have to first of all fetch that using the same procedure we had. So address bus, then read signal, then through the database we will try to fetch the data, so which is this one, right? 42H. So this value is fetched, and then this value and the contents of the register A. So before this one, in the previous instruction we already had stored 21H in register A, and now we have got 42H. These two will be given to the ALU to perform the addition, right? So after doing that, ALU will perform the addition, and CPU will take the data, the result of the addition, and put that into register A. So this is the second task done, right? Now the third task, so similar kind of task, add value 12H to register A. So basically again we have to increment the program counter's value by 2, because already we have completed this instruction, which is 2 bytes in length, and the next value should be 1404H, right? So this will be done by program counter, will be sent to the CPU, right? So CPU will put that value onto the address bus. So similarly, using that address, code will be fetched, decoded, executed, just like previous task. Similar kind of thing. And again, after completing the task, program counter will update its value to 1406H, so which is this one. So again it will try to fetch the contents of this particular location, which is F4H. So CPU will get the data and try to decode that, and it will try to understand that okay, this is halt instruction. So based on that, CPU will understand that now I have to halt everything, right? And it will command program counter to increment its value, so that we are stopping here and our work is done. So this is the overall generalized idea of how a very simple program can be executed inside of a CPU, right? So at the end of this lecture, let us discuss about a scenario where this 1403H contains a value 04H instead of this 42H. So how, because we know that 04H is actually a code, not data, right? But if that value is kept here, how our CPU will distinguish between 04H being a code or a 04H being a data? because in 1402H the CPU already decoded this particular information as an instruction, right? So that instruction was adding a particular data which was stored in the next location with the contents of register A, right? So after it decodes this information or this instruction in this particular location, it will not try to decode the next data we have here. It will always treat the next data or value that is stored in the next location as data. So basically 04H value would be added with the contents of register A, nothing else, right? So that's all for this lecture. Thank you.